Hello, this is Mr. Miller and welcome to video 67, Independent Events. This is the last step in our unit on the rules about probability. Alright, well, we've seen this first formula here several times. This is a formula for conditional probability. The probability of an event A given that event B occurred is the probability of the intersection divided by the probability of the condition B. So we're going to take this rule and we're going to multiply both sides by the probability of B. So if I do that, on the right side they cancel, and what we get is the probability of A intersect B all by itself. And this then is what you get. This is the third rule for probability. So we had one rule for complements, one rule for unions, and finally we have our rule for intersections. The probability of A and B, or A intersect B, is the probability of A given B times the probability of B. It has a conditional probability in it. Now, here's an important idea. If events A and B are independent, I almost said equal, but independent, the probability of A given B equals the probability of A. If they're independent, these things are equal. Okay, so if events A and B are independent, then it just becomes probability of A intersect B equals the probability of A times the probability of B. So this is kind of abstract, but we're going to do some really practical examples to kind of illustrate that. So this is why independence is important. If a sequence of events are independent, then we can just multiply their probabilities. All right, so here's one example we have. It says a new clothing store advertises that during its grand opening, every customer that enters the store can throw a bouncy rubber cube onto a table that has squares labeled with discount amounts. All right, so a little bit bizarre, but this is what it's saying. They have a large table with these numbers printed on the table. Customer comes in, just rolls the cube, it bounces around, and it randomly lands on one of these numbers. And that's the discount they get. So they might only get a 10% discount, but they might even get a 50% discount. All right, so it says the table is divided into 10 regions. 5 regions award a 10% discount. 2 regions award a 20% discount. 2 regions a 30% discount, and the rest a 50% discount. So we're going to use this same problem statement for a couple parts here, a couple slides. It says, what is the probability that a customer gets more than a 20% discount? Well, that would be if it got either of the 30s or the 50. So 3 out of 10, which is 30%. Okay, so a 30% chance that we get more than a 20% discount. What is the probability that a customer gets less than 20%? Well, less than 20 would be any of the 10s, and there are 5 of them, so 5 out of 10. So far, we haven't used our new rule for intersections, but we're going to now. All right, this is the same kind of problem, just a couple more parts. So what's the probability that the first 2 customers both get 50%? So that's the probability that the first customer gets 50% discount, and remember that's intersection, the second customer gets 50% off. Now, these are independent. The first one rolls the cube and gets 50%. That doesn't affect the second guy at all. Whatever the first guy gets doesn't affect what the second person gets. So they're independent. And according to our new rule, that's the probability that the first one gets 50% times the probability the second one gets 50%. We can multiply the probabilities. And that'd be 1 out of 10 times 1 out of 10, which is 1 out of 100, which is 1%. So 1% chance the store is going to give that 50% discount 2 times in a row. What's the probability that none of the first 3 customers gets more than a 30% discount? All right, well, this means that, well, let me see. None of the first 3 customers gets more than 30%. That means none of the first 3 customers get the 50%. So probability of not 50%. The second one doesn't get 50%. And the third one doesn't get 50%. Okay, so that would be 9 out of 10 times 9 out of 10 times 9 out of 10. First one doesn't get 50%, times the second one doesn't get 50%, times the probability the third one doesn't get 50%. And let me see what that is. You get 72.9% chance. Okay, what's the probability that the first customer to win a 30% discount is the 6th customer that enters the store? Wow, so the first time someone gets 30% is the 6th person. So that is the probability that the first one's not 30%, the second one is not 30%, the third one's not 30%, the fourth one's not 30%, the fifth one's not 30%, but the last one is 30%. Excuse me. So, 2 out of 10 are 30%. So the probability that the first one's doesn't get a 30% discount is 8 out of 10. The probability that the second one doesn't get a 30% discount is 8 out of 10. The next one, 8 out of 10. 8 out of 10 for the fourth guy, 8 out of 10 for the fifth guy, and finally, the sixth one is 2 out of 10. So you see we have a sequence of events that are independent. And to get the probability of all of them happening, we just multiply their individual probabilities. We have 8/10, 5 times. That's the first 5 people not getting the 30% discount. Then finally times the 6th one, which does get the 30% discount. If you do all that mess, it's 6.5%. All right, now this gets easier as you do it a couple times and see what's going on. So I get at the beginning it's kind of confusing. So we're going to do a couple more examples. Here's the train problem. To get to work, a commuter must cross train tracks. The time the train arrives varies slightly from day to day, but the commuter estimates she'll get stopped about 15% of work days. So a 15% chance she's going to come across a train. During a certain 5-day work week, what's the probability that she gets stopped on Monday and again on Tuesday? Well, that's the probability she gets stopped on Monday and she gets stopped on Tuesday. We actually don't care about the other days. So that'd be the probability she gets stopped on Monday, which is 0.15, since these are independent, times the probability she gets stopped on Tuesday, which gives you 2.25%. So not a high chance probability that she'll get stopped on Monday and Tuesday. Excuse me. What's the probability she gets stopped for the first time on Thursday? So we have to think about what happens. She doesn't get stopped on Friday, so I put N for not stopped. And not stopped on Tuesday, and not stopped on Wednesday, and stopped on Thursday. We don't care about Friday. So the probability she doesn't get stopped is 0.85. We have 3 of those, so I'm going to say 0.85 to the 3rd power times the probability she gets stopped, 0.15. And this time I get 9.2% chance. Uh-oh, what's probably she gets stopped every day, Monday through Friday? So that's probably stopped Wednesday, stopped Thursday, stopped Friday. Well, we'd have to multiply 0.15 times itself 5 times. That'd be 0.15 to the 5th. So when I do 0.15 to the 5th, I get, it's very small. 0.0000076, which is 0.0076% chance. Alright, so it's not very likely that she's going to get stopped 5 days in a row. So that's fortunate. That'd be a rough week. Alright, one more example. This one's about bowling. So a certain bowler can bowl a strike 70% of the time. That's really, really good. We're going to assume that each time he bowls a frame, what he gets is independent of the last time he bowled. So we're assuming each time he bowls is independent of the other times. Alright, so what is the probability that he goes 3 consecutive frames without a strike? So he goes 3 times and doesn't get a strike. Well, that'd be the probability that the first one's not a strike, and the second one's not a strike. Oops. And the third one is not a strike. So, if he gets a strike 70% of the time, the probability he doesn't get a strike is 0.3. And for this, I get 2.7%. Okay, makes a strike, first strike on the third one. So that'd be the probability of not a strike, and not a strike, and then a strike. So that'd be 0.30 squared for the 2 not strikes times 0.7, which gives me 6.3%. Alright, 2 of his first 3 turns are strikes. This one's kind of complicated because there's 3 ways this could happen. So 2 out of 3 are strikes. So it could be that the first 2 are strikes and the last one's not. It could be that the middle one is the one he doesn't get the strike. Or it could be the first one that's not a strike. So I just threw this example in here to let you know it can get kind of complicated. 2 out of 3 are strikes. Well, we have to take into account there are 3 ways that could happen. The last one's not a strike, the middle one's not a strike, and the first one's not a strike. And when you do all this, we get 44.1%. Alright, what's the probability he bowls a perfect game, 12 consecutive strikes? Well, that means we're going to multiply 0.70 times itself 12 times, which is 1.38% chance he's going to pull a perfect game. Alright, time for the journal assignment. So, do this in your journal, and we'll make sure that we answer any questions you have. See you next time.